Bismillahirrahmanirrahim. So, in last lecture, we have talked about almost the definition of a group, which is that it should have a binary operation, which is enough to say that it is closure. Then it should be associative, and there should be an identity element inside the group, and there should be an inverse for every element. And then we are trying to make like present examples, a bunch of examples, like so that we can actually talk about other things in terms of those examples or by referencing those examples. So previously we have talked about 9 examples where the last one was general linear group with determinant non-zero. So so the 2 by 2 matrices with non-zero determinant under multiplication of matrices, or this multiplication defined here, is a group. Now I'm gonna go forward and talk about furthermore more important example, and let's call it, or like before that, let's say we have one more simple one, example 10, which says that the set of all 2 cross 2 matrices with real entries that set could be in principle denoted by this sign, this notation, is not a group under the operation in example 9. Because inverses do not exist when the determinant is 0. So in this type of sets, determinant can be or cannot be 0. So the inverses do not exist when the determinant is 0. Now, apart from the matrices, let's try to talk about some other example, and that is example 11. So, and this is given by L. Euler from 1761. Now we know that an integer a has a multiplicative inverse modulo n. So we know that, remember, I have done a course on like group theory for beginners, and from in that course, and there is also another course on my channel, Introduction to Pure Mathematics, and those are quite necessary to understand every other course in which I will do in abstract algebra, and in algebra. So if you are doing those two courses, you are good to go to do group theory, ring theory, and other courses, and even representation theory. So we know that an integer a has a multiplicative, inverse, modulo n, if and only if a and n are relatively prime. And what does that mean? That means GCD of a and n is 1. Okay, right. So for each n greater than 1, we define u of n to be the set, to be the set of all positive integers less than n and relatively prime to n. Prime to n. Then u of n is a group under modulo multiplication, or the other way around, under multiplication modulo n. Now let's consider this and try to create an example. Try to create an example where you can actually understand how this is a group, and we will construct the Kelly table for this one. So let's say for n is equals to 10, we have so for n is equals to 10, we have a u of 10, which is nothing but set which has elements less than 10 and relatively prime to 10. So those which has GCD equals to 1. So those which has GCD with 10 is equals to 1. So all those elements. So let's say 1 and 10 divides each have GCD 1. So 1 is there. 3 and 10 have GCD 1. So 3 is there. 2 can't be there. 4 also can't be there. 5 also can't be there. 6 also can't be there. Then 7 and then 9. So these are 4 elements inside it. This is a set. And now we will present the Keller table for this. So we also consider mod 10 as an operation. And the Keller table would be we have 1, 3, 7, 9, 1, 3, 7, 9, and then we multiply these. So the first row would be same, and the column would be also same. Now you multiply 3 with 3, that would be 9, and 9 can be there. So that's it. 3 to 7, 21. Now 21 mod 10 is going to be 1. 27 mod 10 is going to be 7. And 7 mod 7 to 3 is going to be 1. Then 9 and 3. And 9 threes are 27, so that would be 7. 9 sevens are 63, so that would be 3. And 9 nines are 81, so that would be 1. You can see this is, so every element appears once in a row and once in a column. That is the identification of Keller table gives you the group. Okay, perfect. Now recall that okay. Now let's take the group. So let's example 12. The set 0, 1, 2, 3 is not a group, and multiplication multiplication mod 4. Although 1 and 3 have inverses, one and 3 have inverses, the elements 0 and 2 do not, because if you multiply one with one, you will get 1. Multiply 3 with 3, you would get 2. Okay. Now example 13 says the simplest example would be, but like it exclude an operation which is also there. The set of integers z under subtraction is not a group since the operation, guess what? The operation, since the operation is not associative. Which is very rare. Now, you can also present the example from the complex numbers. The complex numbers C denoted is a plus b iota, given that a comma b are real and comma iota square is -1, are a group under operation that a plus b iota plus c plus d iota is nothing but a plus c plus b plus d iota, while the inverse of a plus b iota is just minus a minus b iota. Similarly, the non-zero complex numbers C star are a group under the operation under the complex multiplication, actually. Operation that a plus b iota multiply c plus d iota can be written as SC minus BD plus AD plus BC iota. Whereas the inverse is the inverse of a plus b iota is nothing but one over a plus b iota, which can be written as 1 over a plus b iota multiply a minus b iota over a minus b iota. And when you factorize this, you will get 1 over a square plus b square into a minus 1 over a square plus b square into b iota. So this is the inverse. Okay, perfect. So complex numbers are groups under complex addition and under complex multiplication, but the non-zero complex numbers are a group under complex multiplication. Perfect. Now we can give a very interesting, more interesting one, which is example 15. You can say that for all integers n greater than or equal to 1, the set of complex nth roots of unity, the set of complex nth roots of unity, which can be written as cos a into 360-degree multiply over n plus iota sine a into 360-degree over n, given that k is 0, 1, 2 up to n minus 1. Okay, this is also said that the complex zeros, if you heard of any complex zeros, this is nothing but the roots of this equation, is a group under multiplication, is a group under multiplication. Okay, now let's take a pause and think about these. Okay, then we can also give an example like the set Rn, which is tuple n tuple having a1, a2 up to an in R is a group under component wise addition, which can be something like A1, A2 up to AN plus B1, B2 up to Bn is going to be A1 plus A2, sorry, A1 plus B1, A2 plus B2, and AN plus Bn. Okay, perfect. Now we can move further and present few more examples, but we are running out of them now because this is a complete example class. So I will try to present most of them. The set of all 2 cross 2 matrices with determinant 1 having entries from Q rationals, reals, and complex numbers, or even the finite fields over prime numbers, where P prime is a non-abelian group under matrix multiplication. Remember, matrix multiplication. Okay, and this is called the special linear group. A special linear group of 2 cross 2 matrices over Q or C or ZP respectively. Okay. If the entries are from any F, where F is any of the above, we denote this group if the entries are from F, where F is any of the above. We denote this group by SL to F. And the formula is given in example 9. Now, let's particularly talk about SL to Z5. Z5 Now consider the element. Consider the element A with entries 3, 4, 4, 4. Remember, the entries are coming from Z5, and Z5 only have 0, 1, 2, 3, 4 elements. Then determinant of A is nothing but 3 into 4 minus 4 into 4 mod 5. Okay, and that is going to be minus 4 mod 5, and that is going to be 1. Okay, and the inverse of A, the inverse of A is what? So you'll shuffle these main diagonals and just write the minus 1 divided by the determinant. Now the determinant is 1 in this case, so you will have 4 minus 4 minus 4 and 3. That's it. Now you can't write minus 4, so you have to write that. So that will be 4, 1, 1, 3. And this is the inverse. Now note that when you multiply A and A inverse, it do give you the identity matrix. Okay. Similarly, we can furthermore enhance the question, example number 9, and talk about GLF, GLN, F, or GL2, comma F. And next example, so that is going to be example 18, says that let F be any of Q or C or ZP. The set GL2 F of all 2 cross 2 matrices with non-zero entries or determinants. Sorry, determinants, because we are in GLN. Determinants and entries from F is a non-abelian group under multiplication or matrix multiplication. Is in example 17, when F is ZP, modulo P arithmetic is used to calculate determinants, matrix products, and inverses. So the formula given in example 19, in 9, for the inverse of a general A, B, C, D remains valid for elements for GL2 ZP, provided we interpret division by AD minus BC as multiplication by the inverse of AD minus BC modulo P. And that would be done. So, but like whatever I say to explain that, we present an example. So let's try to solve GL2Z7. Okay, let's take an element, let's say A, which is 4, 5, 6, 3. Okay, then determinant of A is going to be 4 into 3 minus 6 into 5 mod 7, and that is going to be minus 18 mod 7, and that is going to be 3. And the inverse of 3 is 5. So in mod 7, the inverse of 3 is 5. Okay, so you can write the inverse of 3 is 5, is you can say that 3 into 5 is 15. 3 into 5 mod 7 is 15 mod 7, which is 1. Okay, so the inverse of A is going to be the calculation of 3 into 5, 2 into 5, 1 into 5, 4 into 5. And this becomes 1 under modulo 7, right? 1, 3, 5, 6. And A into A inverse is indeed an identity matrix inside GL27, Z7. And if we write that the group GL and F is called the general linear group of n cross n matrices over now the set. Last example would be the set 1 to up to n minus 1 is a group under multiplication modulo n if and only if and is prime. Perfect. Then we can present. So then we can just do is present this table, which says that we have groups here in this line, and we have operations here, and then we have identity elements here, and then we have form of element, what kind of elements we have here, and then we have inverses of elements here, and then we have the information that whether these groups are abelian or not. Okay, and I would give you the time to look at this image properly, and here I will end this lecture.